Bernoulli's equation allows us to mathematically compare the pressure at any 2 points in a fluid, even if there are changes in height, depth, or velocity. His equation looks like this. We are really comparing the pressure at point 1, at point 2 in the fluid. But at point 1, there might be changes in height and there might be changes in velocity. So we include both of those factors into the equation. So we have rho GH that takes into account any height, plus Bernoulli's principle, which is 1/2 rho v squared, to take into account any change in velocity. And then we do the same thing at point 2. If there were not a change in height at point 1 or point 2, then those terms would fall out of the equation. And the same with the velocity. So there are 3 classic situations, and every problem kind of lines up with one of these situations. So I want to try to draw a picture, and I'm going to try to use my mouse, so this is not going to be pretty, but I want you to be able to draw these pictures because the problems are best solved with a good picture. One of the situations is that you could have a pipe that has a change in height. So I'm going to make a change in height. And I'm going to purposely keep the diameter or radius of the pipe the same. So that involves only a change in height. Now I'm going to draw another situation that could have a change in velocity. So like maybe I have a wide pipe that is going to become narrow. So a wide pipe becomes narrow. That would give me a change in velocity. And again, either of these pictures could be flipped left to right, where I'm going narrow to wide instead of wide narrow. And then the third picture is going to have both a change in height and velocity. So maybe I have a pipe. So I'm going to have a change in height. But now I want to make a change in velocity. So I'll make my pipe wide, maybe down at the first floor of the house, and then the pipe becomes narrow at the second floor of the house. So these are some key pictures. On this slide, you can see the pictures better. Let's work through an example of each of them. This example says, water travels a vertical height of 3.75 meters as it travels from the first floor to second floor of your home. Assume that the water flows at a velocity of 8 meters per second through a 6 centimeter diameter pipe. If the water pressure on the first floor is 200,000 pascals, calculate the water pressure on the second floor. These problems are best solved with a good picture. So take a minute and sketch this picture on your paper. The next thing we need to do is draw 2 horizontal lines. I'm going to draw one of them through the middle of the bottom pipe and the other one through the middle of the top pipe. And this is a conservation of energy concept, so we have to have an H equals 0. It doesn't really matter where you put H equals 0, but I'm going to pick the bottom. So if I called that bottom line H equals 0, then I would say that my picture, my problem, involves a change in height. But if you had put H equals 0 on the top line, then you might say that your problem involves a change in depth, which is why I'm using height and depth kind of interchangeably, because it depends on your picture. The next thing is Bernoulli's equation allows you to compare the pressure at 2 different points. So we need to identify point 1 and point 2. So I'm going to put one of my points on the bottom line and my second point on the top line. I'm going to call the bottom one point 1. All right, so let's extract some information from the problem and put it by point 1. So at point 1, we know that the water is flowing at 8 meters per second. It says it's flowing through a 6 centimeter diameter pipe. So 6 centimeter diameter is 3 centimeter radius. And then I changed centimeters into meters. So there's my 0.03. And it says the water pressure on the first floor is 200,000 pascals. All right, so what do we know about point 2? Well, we know it has a height of 3.75. The water has the same velocity, it has the same radius, and I'm looking for the pressure at point 2. So Bernoulli's equation hooks all of this together. Before I start, I could look at this equation, and many times some of the terms fall out. So for example, I do have a pressure at point 1, but there is no height at point 1. So this term is going to become 0, and this is going to fall out. And I do have a velocity at point 1, but if I look over here, it's the same as the velocity at point 2. So these terms are not 0, but because I have the same number on the left and the same number on the right, they're going to effectively cancel each other out, which means that what I have written down here is actually going to reduce itself down to just this statement here. So now I can plug in some numbers. So the pressure at point 1 is 200,000 pascals. I'm looking for the pressure at point 2, and then I still have the height to take into account. So it's water, so pressure or density is 1,000 times 9.8 times my height of 3.75. And my pressure is 163,250 pascals. That's one way that you can use Bernoulli's equation. But the power of his equation is that you don't really have to think that much. If you want, you can just put the equation down and start plugging in numbers and see where it takes you. So let me just kind of walk through this quickly. So I could plug in, I have pressure at point 1, and I could say, oh, I don't have any height at point 1, put the 0 in. I do have velocity at point 1, so I'm going to write that down. I'm going to pause for a second here. This 1/2, I find that students algebraically make less mistakes if they take that 1/2 and turn it into a 0.5. So I'm always going to do that. So I do have velocity going on here at point 1. I'm looking for the pressure at 2. I have height at point 2, and I have velocity at point 2. And so I just plugged everything in. I didn't think too much, and then I just algebraically start working. And yes, I'm going to find out that these two things are going to effectively cancel each other out, but I just mathematically go for it, and I can solve for the pressure at point 2. So you do whatever works best for you. In this example, water travels through a 10 centimeter diameter fire hose with a speed of 1.3 meters per second. At the end of the hose, the water flows out through a nozzle with a diameter of 4 centimeters. If the pressure in the fire hose is 350 kilopascals, what is the speed and pressure of the water coming out of the nozzle? So let's start by explaining the real life situation and comparing it to the picture. So over here we have this fireman who's holding the fire hose, and the whole point of putting a nozzle on something is so that you can take the wide hose and narrow it, and when you narrow the path, the velocity of the water is going to increase. So that's the purpose of a nozzle. So therefore my picture makes a little bit more sense. That I have a hose that's connected to a nozzle, but coming out of the nozzle is the path has narrowed and the velocity of the water is going to be much greater. So I'm going to use this picture, and I'm going to draw an h equals 0. So I'm going to draw my horizontal line, and I don't have any change in height, so I'm just going to call that line h equals 0. I still need to have a point 1 and a point 2. So I'm going to put point 1 in the wide part of the hose and point 2 right at the nozzle, which is the smallest part of the hose. So now let's extract from the problem what we know. So at point 1, it says that the diameter is 10 centimeters. So I made that 5 centimeters and converted that into meters. And it's flowing in the hose with a speed of 1.3, and the pressure in the hose is 350 kilopascals. So I just turned that into pascals. All right, what do we know about point 2? We know that the diameter is 4 centimeters. So I made that 2 centimeters and then converted that to meters. And that's all we know. We're supposed to find the speed of the water coming out and the pressure of the water coming out. So let's start with the speed. We can go back and we can use the law of continuity. So we have point 1, we have point 2, we have this cross-sectional area here. So pi r squared times the velocity at point 1, pi r squared at 2. So obviously those pi are going to cancel. And so I plugged in my values and I find out that the velocity at point 2 is 8.125, which makes sense that the velocity was 1.3, and now because the path narrowed, it's now 8.125, so that's looking good so far. All right, so now I need to find the pressure. And to find the pressure, I'm going to use Bernoulli's equation. And we're just going to talk through it quickly. So we know the pressure at point 1. There is no height difference, so I just put a 0 in there. There is a velocity, so I used 0.5 times water, density of water, 1.3 squared. I'm looking for the pressure at point 2. Again, there's no height. And I do have a velocity. It's a different velocity. So again, it's not going to cancel out this time. And I calculate the pressure and I get 317.8 kilopascals, or 317,837 pascals. Okay, our final example. Water circulates throughout a house in a hot water heating system. If the water is pumped at a speed of 0.5 meters per second through a 2 centimeter radius pipe in the basement, which is under a pressure of 3 atm, so 3 atmospheres, what will be the flow speed and pressure in a 1.3 centimeter radius pipe on the second floor, which is 5 meters above? So the pipes in our house aren't always the same radius. And so I have extracted that the pipe in the basement is fatter than the pipe on the second floor. So that's why I chose the picture that I have here on the left. So let's start by drawing our 2 horizontal lines. One going through the middle of the bottom pipe, one going through the middle of the top pipe, and I need to pick my h equals 0. I always find it convenient to use the bottom. All right, I need my 2 points, so I'm going to pick one on the top line and one on the bottom line, and now let's extract from the problem. So at point 1, we know that the radius is 0.02 meters. We know the velocity is 0.5, and the pressure is 3 atmospheres. So I happen to know that 1 atmosphere is 101,325, so 3 atmospheres is going to be 3 times 101,325. So I have 303,975 pascals. So I'm now looking at the velocity and pressure at point 2, but I know that point 2 has a smaller radius, so 0.013 meters. I'm looking for the velocity. I know it's 5 meters above, and I'm looking for the pressure. So just a little FYI, you can never find the pressure until you have the velocity. So that's why I'm going to do that one first. And we're going to use the law of continuity to find the velocity. So again, we have pi r squared v at point 1 and pi r squared v at point 2. The pi's cancel. And we find out that the velocity at point 2 is 1.18 meters. All right, now we're ready to find the pressure. So I'm going to write down Bernoulli's equation, and let's talk through it. So on line 2 here, we have the pressure at point 1. Since I made that h equals 0, there is no height. I do have velocity, so I put Bernoulli's principle in there. I'm looking for the pressure at point 2. I do have height, so I used rho gh in there. And I do have velocity, and so I put that there. And many times students kind of get lost in the algebra a little bit. So if that happens to you, just a little tip trick that I think can help is just do each of these terms separately and kind of write them down. Do that, take the time to do this extra step, because mathematically it increases your chances of getting the right answer. And the final pressure is 254,404 pascals. There's one more thing that we need to talk about. Bernoulli's equation can also be thought of as a conservation of energy statement, where pressure equals energy per unit volume. So the question is, why can pressure be considered energy per unit volume? So let's look at the units and talk through that. So the unit of pressure is a Pascal, and energy is measured in joules and volume meters cubed. Pressure is also equal to force over area, so that means that a Pascal is equal to a Newton per meter squared. A joule is equal to work, energy is equal to work, and work is force times distance. So a joule is also equal to a Newton meter over the meter cubed. And obviously if we cancel this meter with one of these, we end up with equal units. So yeah, pressure can be considered energy per unit volume. So if we look at it that way, and we say that energy or pressure is equal to energy per unit volume, then this second statement here is potential energy per unit volume, and this is kinetic energy per unit volume. So why is that? So potential energy is normally mgh, where m is mass, but density is mass per unit volume. So this is like mgh over the volume. Kinetic energy is 1/2 mv squared. Density is mass over volume, so it's 1/2 mv squared over the volume. And the same thing for the other side, that these are energy statements and potential and kinetic energy statements at point 2. So the takeaway here is that Bernoulli's equation really is a conservation of energy statement. And that's going to help us in our next lesson.